Great pleasure to introduce Nick again. We'll be speaking on Shtukas and Excursions.
Thank you. So let me try to provide some context. So I guess last time I spoke, I formulated the restricted version of the geometric length conjecture, which is satisfying lots of compatibilities between G's with no support. G. So here we say X is a smooth proper curve. For an algebraically closed field. So this conjecture takes place importantly over an algebraically closed field. And that there's an equivalence between this and the available. What's this? Descriptive. X is implicit in both of these moduli spaces. And so so a theorem a substantial partial result toward this conjecture that was explained last time, I think, is that there's an action quasi-coherent fields. To review some aspects of that, but I think that was the upshot of Nikolai's talk last week, is that there is such an action, and well, in particular, this equivalence is supposed to be compatible with this action. That's not far from nailing down what it is to be. So the goal that I want to set is to extract some arithmetic information. In particular, I want to explain how this kind of spectral action, modulo the trace and its generalization, the Shtukas conjecture, which Kevin will explain next week, it gives an enhancement of ensemble forms. So yeah, so that's the goal. That's the goal. So I mean, how do we do this? So this takes place purely in geometry. There's nothing arithmetic here. Geometry for me means working over an algebraic closed field. Arithmetic means over a non-algebraic. So if X like K bar is D bar, and X is defined from Q, what's the deal? Well, then we have the usual thing, which is we have the Frobenius. Then we have X with fixed point. Frobenius, so somehow going back to the ancient times, the idea is that one should extract in this function field type setting, that one should extract arithmetic information from geometric information and the dynamics of the Frobenius. That's the goal. So for most of this talk, just to simplify things, it's not at least formally, it will really look the same. There's some additional, I don't want to undersell the additional work that has to do with passing from the Betty setting to the Elladic setting. But for most of this talk, would be not in the restricted setting, but in the Betty setting. And so X is over the complex numbers, and the L and so with an endomorphism. So this is what's modeling. So just take an abstract endomorphism, which we should think of as playing the role of Frobenius. Okay, so that will be our setting, and that will be what it's going to be. There's no arithmetic, but there's dynamics.
Are we still assuming that the section fixed points?
No,
No.
arbitrary. Now this is really arbitrary. There's nothing. In this setting, we don't need. I mean, for instance, it could be the identity. That's allowed.
Very high.
That's allowed. But yeah. So the idea. So anyway. So rather than studying arithmetic over finite fields, we're going to study the analogous thing, which is dynamics over complex numbers. All right. So what was the idea is to consider the categorical trace let me try to introduce this idea as mildly as I can. Like there was some discussion of categorical trace as a previous.
It was sketched in the.
Oh, I see. What maybe in previous iterations. That's not come up. Well, anyways, let's just start from the beginning.
At one point, there was a talk devoted entirely to it. But,
Is that
which
right?
is- Yeah, in one of the, you're right, in the previous iteration.
Okay.
So-
Anyway, so the setup, the most basic setup, and then we're gonna start with the most basic setup, and we'll see we're gonna need to work our way up. So the basic setup is that we have something called C, which is a symmetric monoidal category. Category always means infinity category. Well, there is a notion of such a thing, and it is important that it's symmetric monoidal, no less. Emphasize that. So definition. Object is realizable. And there is another object. And maps. Using existence of a symmetric structure here a little bit. Such that satisfying some properties. Let me not we just dramatically, it's a thing that looks like this. So sometimes called Zorro's law.
2 = 1 is called zeros.
Oh, that's a 2. That's a Z. It's a bit rounded. Yeah, so this, I guess the reason for this name is that the symbol, this picture is supposed to remind you of the Marcus arc.
You have to do with one.
Yeah, sometimes, yeah.
Would that be names?
And sometimes people call it the snake. Snake,
No,
yeah. Snake, not snake lemma. Snake lemma is something else. But sometimes people call it the snake identity, which is not great, partly because it's of the conflicting ideas of snake lemma. But I mean, anyway, why is this a lemma as opposed to an axiom? Is because, well, the thing is true for vector spaces. I'll say in a minute. In particular context, it is a lemma. It's true. So that's dualizable. And I don't know. Is everybody okay with this? I can write down what this. Command. Write down actually.
One C means the object.
What's it? One is the tensor unit.
Tensor unit. C.
Okay. So we have that. And then suppose X is dualizable. By the way, a consequence of this definition actually is that X check is the internal on from X to this definition. But well, it need not, I'm not asking for it to be closed, but this thing has to exist. So now suppose X is a dualizable object. And we have some endomorphisms. You can consider we call it the trace of F acting on X. And by definition, what is that? So that's going to be a map from the unit to the unit. So first we apply, I should give these names. This is the evaluation map. This is the co-evaluation. Another name for this is this map is sometimes called unit, and this map would be called co-unit. So we do the co-evaluation map, followed by F tensor identity, followed by the evaluation map back to the identity. So this is an element of endomorphisms of the tensor unit, is what the trace is. Why is this called the trace? Okay, so this is kind of the most basic setup. Definition from I think the 1960s. I believe I'm not sure. Anyway, it's something that I think comes from algebraic topology in that something like the 1960s or something like that. And so, well, let's do some examples. So the first example is, let's take C to be maybe the ordinary category of vector spaces. More fancy. Then X in C is dualizable if and only if it is finite dimension.
Is X check canonically isomorphic to X?
Yes.
Consequence of the X. Okay.
Yes, that is a consequence. It's that. So like duality makes sense in without symmetry, in like a monoidal category. And if you were in a monoidal category, there's a notion of a left dual and a right dual. And a symmetric monoidal category, those are canonically identified. And anyway, I guess in general, the right dual of the left dual is the original thing. But you could get something different if you take like the left dual twice. That's an interesting end of function. That's second, but it's not relevant for today. Everything is, all monoidal things are really symmetrical, aka perfect. But this is saying that like if it's a chain complex, if this means chain complexes, then the total cohomology is finite. This is saying, so I mean, in particular, one first nice observation about this is that if you haven't seen this kind of thing before, is that it gives a completely basis-free definition, basis-free characterization of finite dimensional vector spaces. And now in this case, what is why is price relevant and what is the unit and the co-unit or evaluation and co-evaluation? Well, in this case, X dual, so X dual I said is next to the unit X. So it's the only one field for the time being, and it's so this is kind of really evaluation. I have a K is the unit, and K to here. Well, this whole thing identifies with X, and this is and this picks out the identity. And so, well, I hope it's clear that this map, under this identification, if I identify maps from X to X with this tensor product, then this kind of evaluation map is exactly the trace of the corresponding identifiers. So, well, the trace is really this composite. And so, well, maps from K to K is canonically K, and that element that's a fancy way of taking the trace of a linear transformation. Next, this is important. K, canonically identified with K is the usual trace. That's the way in which this abstracts the usual notion of trace. Okay. This is the basic example, though not quite the motivating example.
So in particular, F is the identity,
Yep.
and this is just the dimension, which is a finite number.
Yes.
In general context, if there's and one dimension.
Well, I mean, you can always take trace of the identity. By the way, notice that here, if we're working in the derived category, then but what you mean by dimension is the Euler character. In particular, it could be any integer, not just a natural number. And so maybe that's less obvious the way I said it, but if you haven't seen this kind of thing before, that's a nice exercise to work out. That minus sign is the source, is the root of all sign problems in homological algebra. The odd ones you have to count negative. But anyway, so it's because of how the tensor structure works for chain. There's a causal rule of signs. That's where that arises from. Yeah, I mean, so in general, you can always take the trace of the identity.
And you can call that dimension.
And you can call that dimension, yeah. I will instead call it trace of the object, identifying the object and its identity. I don't know, just to have a coherent name for things, but yes, another name for that would be the dimension. So really, the main motivating example for this is one level higher. You can look at the category of all categories, PG categories. This has a tensor structure, which certainly has been discussed numerous times. And then lots of things are good. So the higher up you go, the weaker the requirement that something be dualized. So that roughly most things you consider are dualizable. Most. It's of interest. Dualizable. E.g., anything compactly generated.
And you say DG cat and symmetric model.
Nope. No, not symmetric. It is the symmetric monoidal category whose objects are DG categories. Yeah. Rich theory of dualizable categories, and importantly, anything that's pretty much all the ones we're going to encounter are compactly generated. There are some interesting examples of dualizable things that are not compactly generated, but that's not relevant for this business.
Miraculous.
What's that?
Miraculous.
No. I mean, that's also compactly generated. No, that has to do with like self-duality. It's dualizable. See. Yeah, so let me point out something, which is that being dualizable is a property of an object. On the other hand, a lot of times, like especially in geometric situations, what you find is that things are self-dual. But being self-dual is extra structure. And so you can be self-dual in different ways. And kind of miraculous duality is related to that. But that's also compactly generated thing. If you want an example of something that's dualizable that's not compactly generated, is take your favorite manifold and look at all sheets in the analytic topology. That's a.
Is there anything on drive geometry?
I believe that if you take. So first of all, for Arden stacks, I know that even in characteristic 0, quasi-coherent sheaves is dualizable. It is not known in general whether that's compactly generated. In some sense, that's the origin of the notion of dualizable in algebraic geometry. The inability to prove that quasi-coherent sheaves on Arden stacks are compactly generated. And the recognition that dualizable is often good enough. And I think maybe, I'm not sure. I mean, I think a good example to consider is the classifying stack of the additive group in characteristic P. Is that known to not be compactly generated? To be dualizable? Is it known to be dualizable?
That's a good question. Well, it's localization.
Well, everything is a
Something not
localization.
clear because you don't have.
Yeah. I don't know. I suppose that's a candidate. Well, it's not compactly. It's known to not be compactly
I think
generated.
it has no company, no not zero company.
Yeah, that's right. Just like the sheets thing.
Oh, I see.
That's also on a non-compact net.
Isn't that kind of what the second off K theory stuff is about too? It's like.
Well, it's about K theory of these kinds of things.
things.
Exactly. Yeah. Anyway, so that might be a candidate for something in a more algebra geometric that's like that. But anyway, not relevant. Everything here will be compactly generated. But anyway, a good setting is dualizable nevertheless. Well, because we can, for this reason here, is that we can take traces. And so, so if I have a so first of all, what is it? What sort of thing is it? Suppose I have a dualizable category and an endofunctor. I can take the trace. So this is an object in in this category. From the unit here is vect. This K-linear TG category. The unit is what we call vect. And as before, endomorphisms of vect is just a category vector. In particular, the trace here is some kind of a chain complex. You have a dualizable category and you have an endofunctor, then this abstract construction produces for you a chain complex out of it. And well, in general, there's nothing else I can say other than this has a name. So also known as, also called, mention. The Huxham homology. At least in some settings. Let me not write the notation for it. I'm gonna use that notation for something else. So if C, at least if C is A modules and F is given by some bimodule, then this is given by the usual coefficients in a bimodule. Anyway, if that's not a familiar thing, just now you know. Whenever someone says Huxham homology, this is what they mean. Maybe not literally, but logically.
Wait, did you see why this is? It's definition, you can't quibble. No, this is it.
Yeah, sure, let's do it. Suppose C is modules over some algebra, then turns out that the dual category is modules over the opposite algebra. And the co-evaluation map is something that sends K to A as a bimodule. And the evaluation map is the map given by tensoring that same bimodule. So this is the claim. It's easy to check. I guess I didn't write down what the conditions are. But if I did, then it would also be easy to see that this defines this exactly defines the duality data. And then what I get is that if F from A mod, then F of X is F of A tensor over this X tensor over A. Oops. A with X. Then every colimit preserving k-linear functor is of this form. So let's call this M. Then you just trace through the definition. Trace of F acting on A mod. What we get is M over A with A. This is the formula or a formula for Huxham homology with coefficients in a bimodule. Yeah, great. Okay, so that's so the idea is we're going to apply this trace construction to these categories, the left and right hand side. Well, both in the conjecture and more seriously in the theorem. We want to get consequences of the first of the theorem. So let me just say, what the consequence of the spectral action so let me go back for a minute to the function field setting, really this restricted setting. And so, well, if X is defined over a Q, then X has an endomorphism. So that endomorphism induces an endomorphism of all the corresponding moduli spaces by transfer of structure, and that induces an endomorphism of the corresponding categories compatibly. So the upshot is, well, and in particular, on the left-hand side on this quasi-co, it's not just an endomorphism, it's a symmetric monoidal. So what we get is that this categorical trace from Q acting on quasi-co restricted. Check. Well, so this is a priori a chain complex, but in fact, this chain complex has a commutative algebra coming from the fact that this was a well, this trace construction I didn't say, but is a symmetric monoidal trace of the tensor. If you take the tensor product of two dualizable objects and tensor product of two endomorphisms, then the traces will be tensor product of the trace, just like for matrices. And so this acquires, for this reason, this acquires an algebra structure. And as an algebra, this acts on trace of again Frobenius Q acting on the other side.
Just to clarify, what property of probe Q do you use for it to be a commutative algebra object?
Oh, as an endomorphism of this, it's an endomorphism of a symmetric, it's a symmetric monoidal end. Because it's induced by the geometric, by something on its pullback. Well, I don't know. I want
This pullback.
this is pullback, yeah.
Yeah, sorry, just to anticipate what Tom would ask, which Frobenius, this geometric Frobenius?
No, this is no, you don't get to ask that question.
Oh, good, okay. I
I
fumbled when I was asked it.
no, you don't get to ask this question because check this out. There's really only one Frobenius. Well, it is a geometric Frobenius on X. Sorry, you can ask which Frobenius on X. I named you, but it's the geometric Frobenius. And now see, Fluxus restricted is a stack type thing over a field of characteristic 0. It's defined over QL bar. There's no, it doesn't have its own Frobenius. It's the one coming from the fact that it's functorial be assigned to X. It's as I said, it's by transfer of structure. But BunG is of BunG is over a finite field. So you can ask how it compares to BunG's Frobenius. But
In both cases, in all cases where there is a geometric action, it will be geometric.
Yeah.
Okay, wow.
Actually, I have a question because I realized I didn't understand this when I heard you talking. There's some compatibility here, right? Like there are two
Yes,
different
correct.
things called Frobenius.
Yes, that's
right.
right.
So
yes,
there's some additional ingredient beyond just the kind of
yeah,
structure.
that's right. Yeah, I'll say something about what that is. Yes, I mean the Frobenius have to like the two Frobenia have to act compatible.
Exactly.
The that one coming from the one.
But again, it comes from the fact that all where does it come from is, well, the way this is defined is in terms of Hecke operators on this thing, but the Hecke stack is defined just as well over finite. That's the source of the compatibility. Okay, yeah. So this is a consequence. So this is potentially a more concrete statement. So this is some algebra. This is some vector space. And to the extent that we can give these inherent meaning, then we've gained something. And so, well, let me name the meaning. This is a version of the algebra of excursion operators. Enhancement of force. Excursion operators. And this is, well, it turns out that this is just, it's a priori a chain complex, but it turns out that it's actually only in degree 0. And there's only zeroth cohomology of this thing. There's no other cohomology, and it's the vector space of automorphic functions. And this is what's called the trace conjecture. Which is despite the name, is a theorem.
So what do you mean by automorphic functions? These are not hospital or what?
So this is so this
I mean, sub C is cost.
no sub C is compactly supported.
Okay.
So this is compactly supported functions from BunG of FQ
To kilobars.
to kilobar. Yep. Okay. So this is what that is. Oh no, I don't mean hospital. I mean it's this enhancement. So it produce so like if I said literally excursion operators that this is acting on this. This is Song Shui's extension of Laforgue's instruction. So this already this recovers some version of the of Laforgue's spectral decomposition. So anyway, so I think the idea is for Kevin to explain this next time. And
So I'm sure I would say that the subspace of hospital ones are also acting on X.
yeah,
But this is everything.
this is everything. Yeah. So today I want to explain kind of the easier identification, which is this one, which on some level, I mean, it's sort of psychologically nice, but maybe after all of this is well and done, then you should kind of forget all about excursion operators. It's not clear what the morally correct. It seems that the morally correct statement is the thing that's spectral action in this categorical statement, and I'll give and the other thing I want to explain is a refinement of this that involves all of this is zero-legged Shtukas. And really, a better consequence of the spectral action is something about all the cohomologies of Shtukas. The other thing explains how better this is.
Same question as April, is that we use such an action for any endomorphism, like you use Frobenius.
Yeah.
Can you instead take like what did we use that Frobenius here to get this spectral action? To get this action.
To get this action? Let me defer answering your question by about 2 minutes.
This is much nicer. The United States even erasing like razor marks.
Yeah. So okay. So yeah, so I'll answer that a little bit later, actually. But first I want to. Let me do this in the following order. I want to explain this equivalence by itself. And then I'll explain something about this action.
Explain that will take 2 minutes.
What's that? No, that will not take 2 minutes. Don't go too much off the book. So some more examples, some more about prices. Let's get back to there's another example, kind of a sub-example of this. Following. C is still categories. Now my category is not a random DG category, but it's quasi-coherent G. So, so for X sufficiently nice stack, and suppose we have an endomorphism of X. Or X so let's calculate the price of capital F acting on C. So it's the calculation I have to do now. Oh, whoops. And here also, yeah. Okay, well, so for this, I need to, well, let's follow the algorithm. So in this case, finding O of X is actually self-dual. The way it's self-dual is, well, let me write it in terms of geometry, in terms of correspondences, so that the diagonal so the co-evaluation is delta lower star of the unit. The evaluation is the cohomology of the pullback, the diagonal morphism. Whatever nice means it guaranteed. And I should say, perfectly. Answer what? The product. Spencer, and importantly, whatever my assumptions is, are they guaranteed that this is like no, this has nothing to do with Sergio. This is kind of perfect duality. I don't know. This is that if you have a perfect complex, you can it's related to the fact that if you have a perfect complex, you can take it, you can palm into O and get another perfect complex, and if perfect complexes generate good things, this kind of thing is responsible for self-duality. I see. Okay. No, there's no Serre duality. Serre duality would have to do with a corresponding statement frame. That's the categorical duality that encodes Serre duality.
It's a lot less deep.
What's that?
It's a lot less deep.
Oh yeah. It's just saying that. It's a fancy version of the following thing. I told you that if you have A modules, then the dual is A op modules. Now suppose A is commutative, then A and A are the same, and this gives you a self-duality. So in affines, this is what happens, and this is some extension. This from A. Whereas, for instance, their duality on affines is something interesting. I don't like somehow the non-triviality of their duality has to do with how singular your scheme is. That's a local thing.
So nice means affine diagonal.
Nice, let's say, means affine diagonal and quasi-codualized.
I said the same word last week.
Right.
It's sufficient to assume the structure sheet is compact.
Sorry, what,
It's sufficient to assume the structure sheet is compact
for what?
for this standard, like saying.
No, because it doesn't apply like this.
Well, sorry, affine diagonal plus the structure sheet.
So you need to know that the categories. I don't know anything. I don't know any geometric property that implies dualizability. I mean, like, I guess if you're like an arc stack or something. But like, I guess that's an easy functor of points kind of condition that guarantees that the
Oh, sorry, maybe I did affect this part. Sorry, the part stack with that one dag.
yeah, so this is something nice now. Well, let me just say anything. That the only examples relevant for this talk is an affine scheme, modulo, and algebra, and affine algebra. And those are all its nicest. Quasi-code there is generated. And it's compactly generated by perfect operations. And but they remind you where characteristic 0.
Practice, like you're saying, you would dualize the
Well, no, I mean, as I said, I don't. Not really. I mean, for more general hardened stacks, even in characteristic 0, we know that they're dualizable, but don't know that.
So much just write down here.
Yeah, I mean, the easiest thing is to write down the pair. Well, you have this Kuna formula, and which you need to argue somehow. But all examples, let me just say, all examples of access will be an affine scheme, solution to that by an affine algebra. So the upshot is, well, we can compute trace, now we can use base count. Trace. Oh, we can compute in the following way. We start from a point X. Oh, I have the diagonal. Okay, sorry, I read my correspondences from right to left. And then up. X, which is the identity tensor times F, right? We're supposed to pull back along the first factor, then further restrict along the diagonal, and then push forward to a point. So we're supposed to start here and follow this correspondence, pushing by pulling and pushing. And so, oops. And so, well, we can apply base change. This is the graph. This is the graph of F. Composite graph. This fiber product is, well, maybe by definition, the derived fixed point. Fixed points. So the upshot is that this trace this gets identified with functions on this derived fixed point. So there's a kind of a geometric, description in this case of what this is. I mean, in particular, a special case of this is if F is the identity. And this is saying that the Hochschild homology of quasi-coherent sheaves is functions on the derived loop space. The derived fixed points of the identity is the one of the definitions of the derived loop space. Return to them.
Sorry, very idiotic question here. If we just have a standard X, X at point is it?
Sorry, where do you want to X?
Oh, I mean, just, we have it as X at in the upper right. But it's
Yeah.
like we have two maps that point, we push.
Yeah, you pull back, you get O. You push, you have get cohomology.
Ah, okay, okay.
So now, okay, so now let's apply this formula to our, well, and I'm gonna cheat and not do this in the Betty setting rather than the restricted setting, but that's actually not so important. But so the upshot is the following. So mostly I want to avoid the subtleties of saying this, like the same words will pretty much literally be true, said in appropriate order and then interpreted in an appropriate way. Yes, that, so again, for C, we have some endomorphism called phi. What we get is that the trace of the induced thing by phi on quasi-coherent sheaves, local systems, eddy, X, this is the same thing as functions right, just by what I said, and now the observation to make is that this derived fixed points this gets identified with the same kind of Betty moduli space for the quotient. This is the homogeneity quotient. So it's also kind of local systems on something. So so the upshot is that this is functions on, well, these local systems on something else. This thing. I mean, it will also be true here as well, where you have to interpret a little bit more carefully what you mean by. I mean, you can literally take the stack quotient of the geometric curve acting by the Frobenius and then put restricted here, and that will be true.
Then
What's that?
if phi is not an equivalence, you want it to be still so strict, not lots.
Strict, yes. Still strict. So, I mean, the way you can, so to identify, so in other words, so the general feature of this identification of this trace with excursion operators, this amounts to identifying functions on this kind of set with some kind of excursion. So what we'll do is something more general, is just take any homotopy type and identify function and give an identification of functions on the corresponding stack of local systems. So that will solve this problem. That will solve that problem. Almost time for a break, but maybe let me say something. hopefully inspirational, before the break, which is the following, like, here is a way to think about this, how much people over the complex numbers, suppose that P is an automorphism. So if you have a Riemann surface and you have an automorphism of it, one way of building the homotopy quotient of this automorphism is to build a three manifold, which is fibered over the circle. Namely, you cross it with an interval and you identify the two ends according to that isomorphism. And so this becomes the moduli space of Bettian local systems on a certain three manifold. So the usual kind of analogy that you're told between passing from kind of arithmetic type Langlands to geometric Langlands over the complex numbers is that, well, there's an analogy between curves over finite fields and Riemann surfaces, and you do some things. But really, that's not quite right. What this is saying is that the correct thing is there's an analogy between algebraic curves over algebraic closures of finite fields and Riemann surfaces. And the analogy between curves over finite fields to some complex geometry is really to three manifolds. And that fits much better with a story about number fields. So anyway, so really you want to advertise this viewpoint for many reasons, that you should think of the arithmetic thing as like a three manifold rather than a Riemann. Okay, I think now is a good time to take a break. And then after the break, I'll try to pay all my debts.
Right, so I, it's mostly functions of the fixed points.
Yeah.
But it's also functions of the quotient.
No. On this fixed point, the assertion is that this fixed point locus is the moduli space.
The fixed points of the category.
Sorry, there's no category. This is a geometric statement.
Yeah, sure. Yeah,
This is purely a statement in geometry.
yeah, this is.
And it had to do with the fact that phi was an automorphism of X.
Yeah.
I mean, you can just
Right.
the point is that, well,
Yeah.
if you wanted to compute this, how would you do it? Well, you observe that the diagonal map and the graph both come from corresponding maps of X in the other direction. So that whole diagram is local systems applied to some diagram of spaces. And then that thing takes push-outs to pullbacks, the way this functor works. And therefore, this corresponds to the thing on the push-out, and this by definition is the push-out. So that's, you can have him write it. So if this is just an endomorphism, by definition, what this is you do the following. You have X mapping into this gives us so much data. This is what by definition, that's just what I need. And so the point is when you apply this functor in local systems to this, well, that gives you the corresponding pullback definition. That's the reason for this observation. And that's also the reason why the relevant thing is this current book. Well, just identity on both. All right. Great. So let's continue. So our new goal is to understand functions. Let me stop writing. On K is going to be some homotopy type. So this is going to be our new goal, and let me just, to simplify matters, let me assume that it's connected. Wait, what does that mean? That it's connected?
No, yeah, but not that's connected, but like in general, like O sub something. In the algebraic setting, there's a.
Well, this is an algebraic stack.
Sorry.
This is like, but it is a homotopy, but there's an algebraic stack assigned to it, which is many local systems on it.
So you really
Uh,
need global functions.
I mean global, yeah, I mean global functions, yeah. Sorry, this is some abusive notation that is stuck in my head, so. We'll have to live with it. But yes, I mean global functions. Yeah, so one goal is to understand in kind of more explicit terms what this is. And so, well, the point is, well, what do we know? So I think last time it was explained that in such a situation, let me write it like this: B of sub I, so that any connected homotopy type you can write as a sifted colimit.
That was such, I think, but I assume it was not a question.
Sorry.
Yeah.
All right, so where I is a sifted category, and these MI are free, finitely generated, free monoid, let's say. So the free monoid on some finite set. So this is kind of the expression that I'm going to use. So free J sub I. J is some finite set. Well, essentially, then by transfer of structure, what we get
Like you wouldn't be.
oh, well, it doesn't matter. Both are true. No, but no, definitely not abelian. Sure, if you want, I could say group. It won't make any difference. Both statements are equally true. Monoids are smaller than groups, is the reason to maybe take that if you want. But anyway, so the upshot is that what is the upshot here is that this guy it's covariant in this we'll check that this is the colimit. What's that? Say this better.
Oh, sorry, B means class of mine.
B means class of
Sorry.
space, yeah. So this is
Very confused.
so this is a wedge of circles. What's that?
I was explaining.
Oh, yes.
Why you wrote last time.
Oh, yes. So the upshot of this is that, to say the following thing, is that the category of quasi-coherent sheaves colimit quasi-coherent sheaves on just wedges of S1s. So this is and So important, so this equivalence is true both as categories and as symmetric, sorry, in all three senses that you can interpret, either as categories or as symmetric monoidal categories or as monoidal categories. The reason for that is that this is that I is sifted. So those forgetful functors. And maybe let me point out what is responsible for this kind of equivalence. The thing that's responsible for this is that why didn't we want to take just, I mean, we could have written K also the sifted colimit over finite sets. Why did we want these wedges of circles? Is that all of these are connected. And the point is, if you have a map between connected things, the corresponding map between local systems is an affine map. And so this is kind of a colimit where the transition maps are affine, which is what's responsible for this kind of statement. So it's an affineness.
I got very confused about this last time because we had this whole discussion about why you just resolved it to be typed as a sifted column with finite sets.
Yeah,
That's
but you
exactly
need,
for this
you need affinities. Yeah, exactly. You need connectedness for the maps to be affine. Otherwise,
Clear goes through moxis, can in this case be identified with the limit.
yes,
Local systems, but then you want to show that quasi-co on this limit is actually a colimit.
correct.
That
In
requires
general,
some-
that is not true. In general, there's no reason for that to be true. Yeah, in general, what you know is that quasi-co and the colimit is a limit. That's true for abstractly, but quasi-co and a limit is only one way of ensuring that it's a colimit is that if, for instance, everything is affine over. So these are all, you could compatibly pick a base point, and these are all affine over BG check. And basic fact is that if you have a colimit of A modules over colimit of AI is the same thing as colimit of AI modules, as long as the category is contractible. Anyway, yeah, it's the affineness here is really key.
What is the subscript B?
Betty, yeah. Yeah, okay, so we have this.
And that J comes from the curve itself, right? Then we type the curve itself. This is the resolution of the curve. By
Yes,
this
that's right.
lines.
Oh, no, not the curve, the homotopy, this homotopy. Okay, I don't want to, I'm not going to apply to the curve anymore. I'm not going to apply to X. The relevant one is this one. In the arithmetic setting, that's the difference between the étale fundamental group of the thing over the algebraic closure and the Weil group of the algebraic curve. So this is why the Weil group appears.
Bay group having that weird extra factor with me.
Yeah.
Yeah.
Well, I mean, the thing that has to do with Frobenius.
Yeah, you don't care about.
I mean, it's a semi-direct product of the étale fundamental group over the algebraic closure with Z. Yeah, exactly. Which is why this operation is kind of more meaningful. Because that's exactly what that's implementing. Okay, great. So now, what do I want to say? And so the upshot is that functions is the colimit of functions. These are symmetric, all the functors are symmetric monoidal, they take O to O. Well, there's a upshot, they have a map from functions on these wedges. S1s to so and can express. So this can be expressed the colimit of these guys. So, of these kinds of things. So that's kind of a formal consequence of this. So now. So now we're reduced to understanding what these things are and well, how they maybe we'll want to know. So there are two things we will want to know about the algebra of excursion operators. One is like what these things are. We'll see this is where excursion operators come from. And two is how they act on things. And that will be this funny formula. Okay, so
When you see this funny formula, you mean from Bell's and Laforgue's work, that very complicated.
Yeah,
thing
that's right,
the
yeah.
excursion itself.
that's right, yeah. Okay. So that will just arise from formal nonsense.
Wow, okay, excited to see it.
So now we want to study these guys. Bunch of copies of S1. So now let's understand this a little bit better. And so, well, what do we know about this? So let's I think this was just probably discussed last week. So if I take, let me generalize a little bit. So let's take this as a tensor category. Then I think last time there was the assertion that in general, for any k, this is the same thing as this A tensor k, where this tensor is kind of colimit in the world of symmetric monoidal categories. Okay, great. So in particular, I want to apply it to this thing. And so I'll do it in this level of generality. It will really be a statement about tensor categories and what this operation does. But there's a restriction that one has to make. So the key point is that A is rigid. I don't know, is this been considered before?
The word rigidity, I think last showed up in late lecture one about rigidifying stacks. So
No, that's not it at all.
yeah, so.
So this means the following. I get it here yet. So this means the following. One is that the unit is compact. Two, and two is that this tensor product now admits a continuous. Here, continuous means colimit preserving right adjoint strictly A. Let's start A module right adjoint. So let me decipher this. So first of all, it admits a continuous right adjoint. So this is a tensor functor because it's a symmetric. A is a symmetric monoidal category. So in particular, A you can think of as a module category for A tensor A, and then you want the right adjoint to have two properties. One is that it preserves all colimits, and two is that a priori it's going to be a right lax module map for A tensor A. And you ask that this be strict. Alternatively, that this admits a right adjoint in the two category of module categories over A tensor A.
Equivalent to something like being compactly generated by dualizable.
No. There's no compact generation. For instance, you can have something very far from compactly generated satisfying this problem. For instance, take any compact Hausdorff topological space, all sheaves on it. It's very far from compactly generated, but it will satisfy these conditions.
what you said would imply, right?
If,
Classical
definition, if it's compactly generated and dualizable objects are compact, and and all compact objects are dualizable, I guess, and one is a compact object, then such a thing is. Yeah. That's right. So that's a kind of a generalization of the classical definition.
Why is it called rigid?
Well, because I mean, there's a classical notion of rigid where everything has a dual. So in compact objects, everything has a dual here.
So it's not really like the deformation theory.
No, well, it also is. It has consequences about that. But
So what was the core motivation?
what was the original motivation? No, it's because I think it's because some things that are a priori lapsed become strict automatically. I would guess that that's the genesis of this word.
Lax.
Although I'm not sure. The word is classical. To me, at least. So I don't know the exact.
It comes up in like the theory of Tanaka categories, right? Like for representations of a group, right?
Oh, it's rigid tensor category.
Yeah. So this is strictly a
Oh,
generalization.
yeah, correct. Okay.
So yeah, so rigid tensor category.
Rigid. I was assuming that, but yeah.
Why is it called rigid?
What's that?
Why is it called rigid?
That was.
No. I assume. I mean, maybe the name is due to Deline or something.
Yeah.
So I mean, I don't know.
Ask
You'd have to ask him.
Is there a condition in terms of like partial homology vanishing?
I think it's
No, I don't think-
chemical generation. It's in the
I mean, you have to say in what sense. There you can. Well, let's not. Let's not get into that. Let's leave that for discussion at the end. Let's just accept Deline's suggestion. Call this. Anyway, this is what rigid means for a tensor category. And so two. Let me give a convenient reformulation of two. It sort of morally explains a lot of what's going on, is the following. So definition. A functor. And it could be a tensor functor. F is affine if it induces an equivalence between B and you take the right adjoint, apply it to the unit. It's always an algebra object in A, modules for that. Always a comparison. This, and if it induces an equivalence, let's say that it's affine. The functor, and then 2 is the assertion that this multiplication functor is affine. It produces so it produces a lot of questions, the questions about algebras in symmetric monodic categories. Convenient formulation of what this means. Okay, so anyway, so in this case, okay, so maybe
And if A is Q co is the same thing as saying the diagonal is affine.
if A is Q, quasi affine. For instance, I mean, if the diagonal is affine, then that is satisfied. But I mean, more general, for instance, if the diagonal is quasi affine. Well, Sorry, you need to know that in order to deduce something like this, you also maybe I don't know, let's assume that the category is dualized, and you a priori know. Then that implies that the QCO of the product is the tensor. And then it's the diagonal is something like half. It more generally quasi half. But certainly that will imply it. But yeah, this you should think of this indeed as a version of the assertion that the diagonal is some kind of it has some affine.
Sorry, what do you need to assume? Sorry, is the right adjoint automatically conservative? Yeah, I guess that's. I mean, sorry, you were saying that the condition 2 is equivalent to the diagonal being affine, right? But
Yeah.
affine in particular
Implies that this is
the right adjoint is conservative, right? To have that capacity.
yes.
So is it the case that the right adjoint is automatically conservative? Yeah, I guess it is because
It is because you can further compose with the right adjoint to one tensor A, and the composite is the identity. So
beautiful.
the right adjoint multiplication always has to be conservative. Yes.
Great, okay.
Yeah, okay, great. So now. Right, now here's a easy observation. As we have homotopy pushout. Somehow here is what's responsible for excursion operators. It changed what I means.
Sorry, where was I before?
There was I was an indexing category, but I'd forgotten all about it. And now I is a finite set. Plus is the disjoint unit of another point. And the point is, if you look at this kind of homotopy pushout, this is the homotopy. Is the assertion. The homotopy pushout.
That's just a statement in topology.
That is just a statement in topology. Yeah.
Gotcha.
I mean, it's more or less an obvious statement. You know what the word homotopy pushout, you can do this. And so a consequence of this is that you have this A tensor blah preserves colimits. So you have a pushout. So we have a pushout. Tensor categories. Given by A tensor like plus, so this is just the usual tensor. This maps down to A. Let me call this multiple. So I plus. So this you just multiply all the terms. Another one. Plus down to A. This is just A. Let's start this way. And so, well, we are interested in studying endomorphisms of the unit object here. That's what we're interested in. This is some kind of push out.
Where's the full glass get used in that nice diagram?
Here,
Yeah.
right here. I just applied A tensor blah to this whole. I just took this diagram and put A tensor,
Put A to the power.
A to the power, tensor power of it, yeah.
Format.
Oh, you're asking why plus here is needed?
Yeah, it's to make the space more nice.
No, I mean, if I is a one element set.
Mhm.
Then if you just put point here, point, the push out is gonna be point. S1 is 2 points pushed out along. Is a suspension of two.
And it's definitely
Yeah.
clear, sorry, reduction to the case of one.
Yeah, and then,
And you can see it's true in general,
And
something
in
like.
general, it follows from the case where I is a one element set. Because this is a, it's also pushed out in pointed spaces. And there it's a wedge of things, and so it just becomes, and so wedge point is just a point. So it actually is a formal consequence of when I is a one element set. Okay, anyway, so we have this kind of push out diagram of symmetric monoidal categories. And let me just assert that because the fact that A is rigid implies that we have a kind of base change. Like in other words, you go here and you apply the right adjoint here. That's the same thing as you apply the right adjoint here and you apply multiply. So we're rigid. Long as this dagger satisfies base change for right adjoints. The consequence of this is that endomorphisms in this guy, the unit objects, this gets identified with in A, from the unit of A, this is what base change here. So in other words, you start with one here, going to here, that's one, because that's all of these are symmetric monoidal functors. So in other words, this right adjoint applied to the tensor unit here is the same as this right adjoint applied to the tensor unit, followed by multiplication. And then from one here to the right adjoint of one here, that's the same thing as endomorphism. Tracing through some adjunctions. There's a base change assertion, and it follows from it follows easily from this kind of characterization of affine this kind of multiplication affine. All of these guys are also affine. Is a consequence of the fact that A tensor A to A is affine. Okay. Hopefully this is looking good. Because, well, this is now we're seeing some excursion operators, because so if A you check, then what is this? A from one A into oh yeah, this is you take OG to the I.
Well, you check to the I, right?
Check to the, I guess, I plus, and you take the diagonal G invariants. Okay, so these are at least, this is looking good. These are like the pieces, and the whole algebra is a colimit of these.
So do you have any insight into how Malson before actually constructed the excursion operators with these tracing sort of like these sorts of invariant, like was it something like this maybe, or
No,
was there
I
some
think there was a
inspiration?
more, I don't know, I think there was a more classical statement I mean, he cited, I mean, I think there's this work of Richardson.
Right, no, but I mean.
Which is about, anyway, and I think he extracted some, I don't know. I don't, I should not speak to what was in Vincent's head.
I tried to extract it from Brinfeld and
Uh-huh.
said, I don't think about excursion operators. I have no.
Yeah. But anyway, but abstractly, so here is the genesis, kind of from this point of view. It's very natural.
Yeah.
Okay, so now let's keep going. This is what?
It's then the product, right? What kind of power is it?
Oh, yes, sorry. Yes, tensor product. So, great. So now, so these are kind of global functions are built out of these. And so the basic thing is, how do these act on sheaves? These sheaves. So the other theorem that I think was maybe discussed last time is a description of this category of quasi-coherent sheaves. Not in these terms, but in different terms. That exactly comes from resolving K, not by wedges of circles, but by finite sets. Is that functors actually functors A tensor K to some category do the same thing as families functors A mapping to C tensor local systems on K to the line.
These finite sets don't have anything to do with K, it's the way to resolve K by finite sets.
No, these finite sets don't. The way you prove this, the way you prove such a statement is by resolving K by finite sets. So in some sense, you can reduce to where K is a finite set, and then there's an easy argument there. But I guess this is I guess probably Nikolai didn't make this statement, but made the statement of what it means for this thing to act on. But it's the same argument shows that.
I didn't actually explain how you see this equivalence.
Well, okay, I mean, I don't think I want to spend the time to explain this equivalence either, to explain how you see it, other than to say that, you can pretty easily and formally get this by resolving K by finite sets. So you just express K as a sifted colimit of finite sets, and then there's some games you can play, which gets you to this.
And this proof only works in the Betty set.
And that proof only works in the Betty set, yeah. Oh, on the other hand, the corresponding thing is true for restricted local systems. Kind of the same statement that I think you mentioned implies that. So see, this is a statement about this tensor K. There's a corresponding statement about where you replace tensor K by this cohom, and that will also be true.
Sorry, what is C here?
C is just some category.
Okay, so it's just arbitrary.
Yeah, just arbitrary functors. And so, so A tensor K, so A is rigid, remember? This doesn't really use rigidity, but now let's assume that A and A tensor K, well, A tensor K will also be rigid. And this, in particular, this is subdual in the canonical way. So let me. Running out of time, so let me not say much about that, other than there is a canonical self-duality. It's sort of what you can imagine. If you think about the example that A is quasi-coherent sheaves, and you rewrite that in categorical terms, that will give you the duality. That will work always for rigid. The self-duality that will.
Just a secondary question regarding
Yep.
a little bit earlier when we got the excursion operators class
Yep.
formulation. Is it possible using this to see as one of the problems with the original sort of language setup, right, was that you couldn't, was that excursion, if you only used Shtukas with 2 legs, right, that was sort of Frobenius compatibility or something like that.
Yeah.
And if you had to have arbitrary numbers of legs, and that gave you the full excursion operator compatibility.
Yeah.
Is it possible to see how many legs, as it were, from this sort of formalism are required to rigidly determine the sort of unique multiplicity 1 type formula?
No. No, this is too formal for that. Those are more subtle.
Okay,
What
so
you're
it's like-
what you're asking.
The number of generators, pi 1x or something like that.
No, what you're asking is a much more subtle question. This is very coarse in general. I mean, this is really abstract nonsense. They're not gonna. The kind of questions you're asking about are, I think, are deeper.
I see, okay.
I mean, all of this in some sense is really abstract nonsense. And there's only so much you can get this way. You need some non-formal input to get non-trivial statements. It's rich. Okay, yeah, so the upshot is that, I want to think about is elements of A tensor K are functors, are families of functors from A into local systems of K to the I. So this is, strictly speaking, this is functors from A into that, but because of the canonical self-duality, that identifies that with objects. That's like an object of the dual category. And because it's self-dual, via the self-duality, that gives you an element of A.
That's sort of obvious, just. Is
what
what
obvious?
Just say that at this point, would this be obvious, or
What's that?
is the upshot here in itself sort of clear for general abstract reasons without any of the prior?
No, I don't think so. No, I don't think so. No, because you see, this. I don't know, well, depends what you mean by abstract reasons. So this as defined has a universal property as a symmetric monoidal.
Sure.
Like like this thing, and I'm saying that like if I give you an abstractly defined symmetric monoidal category with like by a universal property, well, okay, that means you know how to like map into or out of it by symmetric monoidal functors, but that's not the same as, that's different than like being able to name what the object.
I see. In some sense, you could have, in another alternative history, defined this definition.
Yeah, I could have, but then I'd have to define all this other stuff. I have to define the tensor structure on this. I'd have to, anyway, I'd have to do a lot more work. So, but it's some unraveling of this definition. Again, it involves. I mean, one way of proving this is kind of resolving K. Although maybe that's not the best idea, because that's the thing that works in this Betty setting. There's a different argument that works in more generally, that's relevant for the restricted setting, that in some sense has more to do with resolving A. So and maybe the thing, so for I, so this is 1 and 2. is given in this collection, A sub I. This collection as an element of A tensor K dot com from the unit into this thing. There's just some unraveling of duality here. That this is exactly the value on the unit of for the empties. It's this A sub empty set of the unit. Inside of, so this is local systems of the zeroth power. So that's local systems on a point, which is vector. So this is what computes, abstractly, what computes global sections. And so now the assertion is,
Vacuum module with respect to legs.
yeah, that's right. This is the vacuum module with respect to length. Yeah, so already, by the way, this should remind you of the structure you get for Shtukas. So running a bit out of time, and so the claim proved is that these guys, A, 1A to or 1, they act on this. So there's a this is an algebra, even though it's not written as such. This acts on one into this guy via the as excursions. You'll allow me, I'm not going to write down the formula. For what this is, it's the, I think this appeared in some talk. Yeah, the formula.
Oh, the really long formula?
Yeah,
Oh, yeah,
that's the really long formula. So it's just kind of unraveling.
that is the excursion.
Yeah, the excursion. Yeah, so it's just that one. I mean, I could write it down. I'm not sure it would be. So
So the technical thing one has to actually then check is the heck of the
yeah. I mean, we're not. I mean, this is just some abstract state. Sorry, I'm not done.
Oh, okay.
We're not done. There's a
Polar horses.
yeah. No. So far, nothing happened. In some sense, nothing happened because everything. So, you say this word hecka, but really, everything I've been talking about is taking place on the spectral side so far. And this is just a purely abstract way of defining what sheaves on this moduli space of local systems is just functors like this, and extracting out of it how the algebra of global functions acts.
Oh, so we haven't even verified that the automorphic space agrees.
Well, there's no automorphic space in the picture yet. So so the last thing, so the thing I want to explain in the last few minutes, the thing I want to explain in the last few minutes is how to get these kinds of things as cohomologies of Shtukas arising naturally from the spectral action.
Just these families, it's from A tensor I to the power, right? Is the domain.
Oh, sorry, yes.
And in the
Yes, thank you.
formula written above as well. Family is A tensor I. Okay, great. Yeah.
Yep. All right, about that. Absolutely. I mean, it has to do with the following thing that.
Something about something twisted arrows, right?
No, the twisted arrows comes later. In some, well, I don't know, there's different order in which you can do twisted arrows. I mean, the twisted arrow, one way of saying where twisted arrows comes from is to formulate the sense in which this is factorial enough.
Right, like natural transformations are
Yeah.
given by some limit over twisted arrows.
That's right, yeah. From this point of view, it comes later. There's a different perspective in the long paper where the twisted arrows come first in a different way, where they arise Yeah. Whoops. Okay. Took longer as always. So now. In the last. I don't know, when am I supposed to stop? Am I actually supposed to stop at the hour?
No,
or-
I, 6:10.
What's that?
You can go to like 6:10.
Okay, yeah, so the thing I want to explain is how the spectral action gives you a collection of functors like this, which have something which are given by cohomologies of Shtukas. So for that, we have to first talk more about traces. More. Traces. Oh, well, what more is there to say? What more there is to say is that so far we were talking about traces in a symmetric monoidal category, but now I want to talk about traces in a symmetric monoidal 2 category. Now C will be a tensor 2 category. 2 means infinity. So there's some 2 morphisms. And so what the new feature is, so there's still just as well the notion of a dualizable object. It's the same definition. But now, if X and Y are dualizable objects, like what's the novel feature here is the following: is a trace takes an endomorphism of a dualizable object and produces an endomorphism of the unit. And now what you're allowed to do in 2 categories is you're allowed to ask for the functoriality of this. In other words, you can ask under which circumstances, because endomorphisms of the unit now forms the category, you can ask under which circumstances the trace construction gives you maps between traces. This is now a meaningful question. And the answer is like this. So I have kind of fx, x to x, and fy, from y to y. And suppose we have, I don't know, p from x to y. And the condition, the most important condition is that this map, to induce a map on traces, it has to admit a right edge. Which is also a thing that makes sense in a 2 category, a right adjoint. And
In one category, what would be the analog of this? Just the inverse, or
what's that?
in one?
In one category, it would just be saying that it's invertible.
Okay, good. So it is the inverse.
So I mean, it's like if 2 things are isomorphic, then there's traces. More precisely, if you give an isomorphism between 2 objects, that gives a path between their traces. Gives an isomorphism between their traces. So and you have this thing, yeah, x, b, y, y, b, x, y, and you want 2 morphisms in this direction. This induces, check, this induces a map, trace phi. Induces a map from, I don't know, let me call it trace phi from trace fx on x to trace y on y in the endomorphism category. This is the so this is kind of the novel feature about traces in 2 categories. So let me give you an example. This So the main example is going to be the turn pair. Example of this. Suppose C is again. You can't, that is naturally a two category. Allowed to do that. And I take some dualizable category. For the moment, let me take these F's to be the identity to simplify notation. And suppose and let E and D be a compact object. So saying an object is compact is the same thing as saying there's a map from the unit to D. Well, that's any object. And saying that that object is compact is the same as this functor admits a continuous right adjoint. In other words, it admits a right adjoint in this category. D admits right adjoint. So by what I just said, this implies that I get a map from trace of that to trace of D. So this is just K. And this, as we said, was whatever it is, trace of D. I cannot use this. I'm trying to reserve this notation each age or something else. So this gives you a class. So if this is the Hochschild homology of D, so this is a way of starting with a compact object and producing a class in Hochschild homology, which is the term character, the version of the term character. So now, what I want to do is do a kind of a souped up version of this. Second example, and C is going to be what's called the Morita category of DG category. So objects are monoidal DG categories. Morphisms, very imprecisely, are bimodule categories. Two morphisms are just maps of functors of bimodule categories. Yes. Great. Clear.
So by module would be another
A category with an action of A tensor B with the reversed multiplication.
Should look like in fact it's three.
It will in fact be a three category, just like this was. We originally took it as a one category, but it's really a two category. But the three categorical structure of this is irrelevant. We're not going to use that. There's some other three category that's relevant, not this one.
Is that as high as we're gonna go?
Three?
Yeah.
Yeah, I think so. At least for now. But well, I mean, today, no, today two is as high as.
But in the big paper, three.
No, but well, there's three that appears in GKRV. There's no three that appears in any of the other papers.
Game three authors lose.
Lose
Lose a three.
A two.
Oh, no, you're right now. Numbers don't work out.
Anyway, so then every object is dualizable. And I don't know, I'm. The fact, let me say it like this, is that, and so let me call A, so here, let me call trace in this Morita of A is a monoidal category, let me call this HH of A. It's a little bit closer because it's like an algebra object in something, and I'm taking the Hochschild homology. So I mean, this is literally A tensor A tensor A. Writing rev for reverse multiplication, not to be confused with the opposite category. Okay. So that's what that is. And so the fact is that if A is a symmetric monoidal category, this Hochschild homology of A, for instance, this is what we previously called A tensor S1. And more generally, if I have a map T from A to A, then this Hochschild, this funny Hochschild homology of A with coefficients of the T. So this is a symmetric monoidal functor. This is this kind of funny homotopy quotient. Try to, in the sense that was before. Okay, great. So now, so that's one fact. And so one thing you might ask is if so, what we'll be interested in the whole game. Since the main technical contribution of this paper, or author paper, is about relating this kind of trace to the previous kind of trace. So this, in the case that A is a rigid category. So suppose A is rigid. If A is rigid, we have is, well, let me write it without is the trace in the sense of DG cat of A. So this is a rigid is in particular self-dualized. It's dualized, it has to be dualizable as just a DG category. So this is some chain, some vector space. So this gets identified with endomorphisms inside of A category of the unit. So this is one fact. Sorry, I'm not putting in the endomorphisms anymore. Say on notation. But you can, if you have something acting on it, then same thing. But the thing that's acting over here. And moreover, here is the key construction. Suppose A acts on some category M, and then A is rigid, implies that M is dualizable as A module category if and only if M is dualizable. Like as a DG, just as a DG category, for getting the action of A. And so just applying, so M gives a one morphism. The unit into like, I don't know, A, I don't know, let me call it A mod. In this Morita category. And so we can take its turn class. Turn class. What it does is it gives an object called trace enhanced of M in this functional homology category. So the point is, like, why is this trace enhanced? What's enhanced about it? Well, it's an object of some category. And the point is, oh, wait, hang on, okay, I really should wrap up. The point is that this thing knows about all the traces. So here is the example of it as a theorem, which is that suppose, so A acts on M. There's also a thing with compatible endomorphisms. Let me suppress that for just to ease notation. So this is dualizable. So here's what you can do. You can take an element, you can take an object of A, and you can study the trace of its action. A is a functor from M to M, just given by tensoring by A. H is supposed to be a suggestive letter here. For action. Or Hackett. H here is A is an object. H stands for Hackett.
So this is the theorem you promised to show us 2 minutes ago.
Yeah. Two is time dilation. So this acting on A. So if you take A to be the unit, this is just the trace of A. So this is just from in this functional homology category from the unit into A tensor trace enhanced of M. So there's a natural functor from A to functional. A naturally acts on the functional homology category. And so this is that action. So in particular, it's completely recovered by this. Everything is all of these things are completely recovered by this trace enhanced. That sort of is the best thing. Is the version of trace that knows about traces of all of these things at the same time.
What is the eighth M?
Is one of the A. Oh, this is M. Yes, thank you. Yep. Yeah, so this is
Where does trace enhanced live?
trace enhanced lives in this category.
Okay.
Yeah. Okay. So now let's return to and now we're ready to return our situation where we have the spectral action. So this is for X. This is X on G of nil on G. So we have this action. And now, so rather than taking trace of Frobenius, we can take trace enhanced. Whatever this is an object in, well, trace this functional homology version of this, which, let me just say, is so this is an object. This produces a quasi-coherent sheaf on this thing. And now, remember, almost done. So this is kind of remembering all of the traces of all the Hecke operators as well, not just the identity line. And now what we have, remember what we have. We have a concrete description of this category. We have, so this gives a collection of functors, family of functors, from oh well, what is that quasi-coherent sheaf here, right? We said that already. So this is a family of functors from rep d check to the I to local systems on this X mod from and so on. So well, and the so unraveling and applying that theorem, a version of the theorem, that one about trace enhanced. It gives the following thing, that the composite functors so there's two things. Functors so you can pull back along this quotient, and to descend is exactly giving compatibly. The descent will have to do with the partial Frobenius structure on this functor. That's the descent data for this thing. But this will be the following thing: is that some representation. This goes to, I don't know, X. This goes to some local system where the fiber at X is the trace, is this categorical trace of the Hecke operator corresponding to X and V, composed with Frobenius, acting on this Sheaves nil. So that's more or less a formal consequence of this kind of compatibility. I guess slightly souped up version of this compatibility tells you that this has that description. Now the point is, well, really. So this is more or less. So let me ignore nil and let me pretend that Sheaves has the property that the categorical Kunath formula holds. So maybe let me say the Shtukas conjecture is that this trace is the P in the very uncarefully passing between this is really in the arithmetic setting, is the cohomology. Of the I-legged with coefficients corresponding to B, with the sheaf corresponding to B. under Satake. So let me try to, so let me pretend that this sheaves nilp is not there, and that I can do this in the geometric set. So how does this work? I have the Hecke action. So the Hecke action is my Hecke stack, which goes to BunG times BunG times X, and I'm trying to compute. Well, maybe like this. G. Maybe let me write it times X. Everything will be over X. G times X. I have this correspondence. I want to compute. I want to compute the trace. Well, so how do I compute the trace of something given by push-pull correspondence? Well, I pull back along the I intersect it with the diagonal, but I have to take the composite of this with Frobenius. So there's prob X. So in other words, I have this is sub I. So the point is, I have this Hecke sub I going to BunG times BunG times X to the I. And I'm supposed to pull back along BunG times X to the I, where this is identity comma frob. And I'm supposed to take the kernel here. The kernel is given by the Satake thing. And so notice that this is exactly, this pullback is by definition the moduli space of I-legged Shtukas. So I take the corresponding sheaf here, corresponding to V by Satake. I pull it back and I take its cohomology. That's what this formalism suggests should be the case, as long as there's a kind of a nice correspondence between geometry and sheaf theory. For alectic sheaves, that's not true. That's why there's a non-trivial content to the Shtuka conjecture. In the Betty setting, there's still this, I guess there's still this issue of putting nilp in, but anyway, without nilp and assuming this Kunith formula for sheaves, this naturally you expect it to naturally produce this thing. Okay, well over time, so I'll stop here, but this is the way that Shtukas naturally arises, traces.
How far is it from the classical definition?
This right here is the class. This fiber product. This is the, yeah, that's the definition.
There's full conjectures about some kind of connectivity with base change. Or...
No. It's much more. It's a pretty deep statement. I mean, the
base, you were saying that there is correspondence.
No, the issue is this. So in the alectic setting, two things fail. One is that it's not true that the tensor product of alectic sheaves, that the alectic sheaves on a tensor product is the tensor product of alectic sheaves. That's the first thing that fails. So this kind of passage from geometry to sheaves is only suggested. That's thing number one. And maybe even more seriously, is you need to keep track of this nilpotent singular support. And that's the that's sort of the thing that makes this question difficult.
But do I understand correctly that you gave us a moral explanation, which is kind of
yes, this is a moral
technical.
Well, I don't know. It's more than technical. Like you have to explain nil. I did not give you any moral explanation for nil.
Yeah. No.
And the point is somehow the point is, well, let me say it like this. So there was a trace conjecture, and the way the trace conjecture is proved is really by proving the Shtuka conjecture. There's no way to. I don't know any proof that doesn't first prove. Like, by the way, the trace conjecture is a special case where I is the empty set. If you take I the empty set, that's the trace conjecture is literally that. So that's the Shtuka conjecture for zero-legged Shtukas. I don't know how to prove it without proving the whole thing. That's point number one. And point number two is that the way it's proved which is the only way I know in that paper, which is the only way I know how to prove it, is that even though it's completely a statement about BunG, it's completely a statement on one side, it uses the Langland's duality and the spectral action in an essential way.
So it's that first point you said, which is that L-adic sheaves tensor products don't.
Yeah.
That is related to this partial Frobenius thing, Grinfeld, right?
No, the partial Frobenius is, well, it is, well, sorry,
One of
yeah.
a product is not.
Yeah. Well, really, where you see the partial Frobenius in this story is in the descent from here to here.
I see, okay.
This is what partial Frobeniuses do for you. I mean, the fact that, anyway, that's a slightly different thing. I mean, this Drinfeld, the reason that this Drinfeld thing is subtle is because of that fact. But the partial Frobeniuses you would have even if you don't. I mean, you can still make sense of, like, imagine like you're in a topological setting and you have some automorphism of X. Then you still have a version of partial Frobenius where you just act on some of the factors. So that in itself is independent of the fact that this tensor product fails. But yeah, anyway, but so somehow these two problems, in the end, these two problems cancel out about having to keep track of nilpotent singular support and this failure of the Knuth formula categorically. But anyway, but the proof is involved. The proof uses Langland's duality. Perhaps there will be a better proof in the future, but one can try to imagine various things. But at this point, it's proof using the spectrum, the full machinery of the spectrum. And everything will be explained next week.
Leave for speaker again.